Okay, guys, let's get started. So first thing, I just wanted to give you, let's do the usual quick review. And so we said, we have this thing called a bipolar transistor, and it's a three-terminal device and emitter. And we said that if you bias things up correctly here, which means that so you'd like if you put it in a forward active mode, if forward active mode, and what does that mean? That means the base emitter junction is forward biased, and the collector base junction is reverse biased. If you do that, so if you put a voltage source here, say emitters in this mode is connected to ground. So if you put a VBE here, that's sufficiently high to turn on this base emitter junction. So let's say we make this VBE 800 millivolts, which if you guys remember, so this is kind of roughly around, like a VD on of a PN junction, right? Like a diode. And then if we put in a voltage on the collector that's high enough, let's say if this was a volt, then the difference between plus and minus here would be 200 millivolts, because this node is at 800 millivolts. So if this node is at 1 volt, we got 200 millivolt reverse bias on the collector. So something like this with these values would put this in forward active mode. And if we had that, we said that we calculated what the sort of a simple model is. There is a so this is a three-terminal device. So this is an emitter. This is the base. This is the collector. And so if we did all this stuff, this collector current would be I sub s exponential of VBE over VT. And we said this would be a really good thing because now we can use this as a gain element or amplifier. If we did, there's a bunch of things you can do, but one thing you can certainly do is put that external resistor across this and get like voltage gain, potentially, depending on where you are. And then so you get basically this exponential change in collector current with the input voltage. So VBE acts like the input voltage, and this current I sub C acts as a output current. Okay, so that's where we were. And then we said that I sub S, I sub S is proportional to the area of the emitter.
Professor, I have a question real quick.
Uh-huh.
I have a question real quick. It might be a dumb question, but if we were to look at a wiring diagram, would we see like what you drew at the top of the page here with the input at the base and emitter and collector? Is that the symbol we would see?
That is the symbol you would see. Yep.
Okay.
You would see a bipolar transistor. Yep.
Okay, cool. Thank you.
So let me do this. Just give me 1 second. See if I can pull up like a schematic from
Oh, it's okay. You can continue. I was just curious if that's what I would be looking for.
I mean, I think that's a good question. Let's see if we can. If I thought I had one. Okay. Let me see if I can share my screen. Share screen. Okay. Share. Okay. So you guys see a bunch of bipolar transistors now here
Yes.
on the screen? Okay, great. So so a lot of times what happens, so by the way, my wife who's also an electrical engineer, was expressing to me her frustrations because in the microelectronics classes, you start learning about transistors, but then, a lot of times when you get to labs, etc., you start actually using, and you learn about these like operational amplifier, etc., which are collection of these transistors and collection of these devices, because you rarely have, as it turns out, you can start, we're looking at a single bipolar transistor and a single resistor, but the more, it's not always the case, but a lot of times the more of this stuff you put in together in one unit, you can get more good stuff happening. And I'm not going to get into that yet, but this is an example of an operational amplifier, which is like, this is a very, very old one, and it's like just like a home run. Whoever designed this, the 741 op amp, that, like, when I was going undergrad was old, and I bet you guys are still using it in the lab, or if you take a lab, you'll use it. And so, I haven't counted. I guess it says here, so there's like 20 bipolar transistors here. And what you'll see is, so you'll see some of these topologies, so it looks very confusing, but this is kind of the stuff you'll see. This is a bipolar transistor, this is a Casco. There's different structures here, but sort of that's what you'll see in a schematic. You'll see resistors, etc.
Professor, can I ask you a question?
Sure.
Is there like is there a method to kind of like see what the transistors are doing? Kind of like the diode with the ideal voltage model. Like you said, we have a VD on, and if it turns on, it's on. Is there something similar to that with the bipolar transistors?
Can you say that again? Are you talking about like in terms of if you had something like a diode, you'd have a switch, or is it like, can you rewind and ask your question again? I'm not sure I got
Yeah.
it.
Yeah. So my question is there a simple way to analyze a circuit like this just by observation? Like, remember with the diode, we would
Yeah.
have the ideal voltage model. So is there some simplification way similar to that one where we have analyzing with transistors?
Yes, there is. Except it's gonna take a lot more experience for you guys to do it. Actually, that's a really good question. So what happens is, you'll see over and over again similar topologies, and you'll start like recognizing them. So for example, so like look at this pair here. And
Yes.
so this pair is like a current mirror. I'm not an expert in this like op amp. I don't like, it's like the first time I looked at it in like years or whatever, but I can immediately tell it's a current mirror. So what you do is, there's a bias here. Okay, this pair is getting a bias current going through here, and that current gets replicated, puts into this input stage, and here's another current mirror here. So basically start recognizing common topologies. And so op amps, for example, usually have differential inputs. So you see this input differential pair. Don't get too confused here, because I'm like, there's a lot of stuff happening here, but this is like an input differential pair. This is a common emitter stage. This is like a high impedance output load. So it's like I can immediately see like common. This is like a normal out. This is a sort of a push-pull output stage. So it'll take experience. In fact, if you try to sit here and analyze this thing without sort of recognizing those those common structures, it'll take you a really long time, and it'll get very confusing. But what will happen is, as you build your knowledge, you'll start basically learning, let's say, how this current mirror works, and then from then on, you just start recognizing it the more experience you have, or how this differential input stage works, or how these loads work, or how this current reference circuit works, or how this output structure works. So the classes, as you take more microelectronics classes, and as you do more microelectronics projects or use them at work, you start recognizing these structures, and you'll recognize, like, well, this capacitance is important here because it'll give me, it's stabilizing the internal pole of the stage, that kind of thing. Does that help? So like this, something like this does seem like just a jumble of stuff, probably, to you guys, but like I can immediately see just experience and taking the classes and stuff. Does that help?
Yes, thank you, Professor.
Sure. Okay, so yeah, but anyway, this is what you'll see. You'll see like actual bipolar transistors. So these are the NPNs. You'll see these arrows coming out. When the arrows comes out of the emitter, it's an NPN. And if you guys remember, I said there is something analogous to an NPN, which is a PNP transistor. So that's a PNP. And it has, like, everything is like almost the same as an NPN, except all the voltages and currents and everything is kind of inverted. And it has a bunch of uses why you'd have that. We're going to look at it maybe in a couple of lectures, just sort of in passing. Most of the time we're going to look at the NPN. So NPNs, PMPs, the rest of this, resistors and capacitors and stuff. Okay, so let me go back. Just 1 second, guys. Start running it. Okay. Okay. So back to this thing. Once we're like in this forward active mode, we get this exponential collector current with input. We learned that the I sub S, which is a key parameter, usually, when you buy a bipolar transistor or see a bipolar transistor, by the time it gets in your hands, this I sub S is like a single number in the spec sheet. And so that is dependent on the area of the emitter. So that means if you put two bipolar transistors in parallel, you'll get, 2 times I sub S. You can just pretend it's like one bipolar transistor, but with twice the I sub S if you connect it completely in parallel. So that's where we were. And then, so now today, I'm going to do one more example out of the book. And then we're going to start looking at basically, the base current and the emitter current. Okay, so let's see.
A quick question.
Yeah.
The direction of the current is going or is pointing down because the collector is higher in potential, right, than the emitter, respect to the emitter.
Yes. Yes. So if you're let's see. So let me. So this is kind of a very theoretical way of looking at it. So let me like draw an actual bipolar transistor, like the actual what it would look like. Okay, the circuit. It would look like this. So I would draw the bipolar transistor and put the VBE here. and then I would actually put the resistor to the collector like that. And so remember, if you had a, whoops, sorry guys, you have this NPN structure with this being the emitter.
Professor, I think you stopped sharing.
Oh, thank you guys. Thank you. Sorry about that.
First.
So let me draw this guys for you guys again here. Sorry. So what I was saying was that this thing is like a kind of a theoretical thing. So let me just draw this schematic. So I'm going to draw something like this again. Now with the resistive load. So this stuff stays the same. But then the resistive load sort of goes like this. Okay, and why is that? So let's look at the direction of the currents, etc. So if I was going to draw this like our sort of semiconductor sandwich thing, NPN, where this is the emitter, this is the base, and this is the collector. Now remember that what we had was we had a bunch of electrons. The collector current was a bunch of electrons that had left the emitter, gone through the base, and ended up in the collector. Okay, so that's a bunch of electrons going in this direction. Now, the way we define current is because we define a positive current as being in the reversed direction as the movement of the electrons, because electrons are negatively charged. So if you look at a collector current going through here, it would be going, so the current from these electrons would be going in this direction. Although the electrons are moving from the emitter to the base to the collector up, the corresponding current, it's just sort of conventions of sign. A positive current is going in the opposite direction. Okay, so the current would be going this way. So the current would be going this way when we draw it as a current. Does that make sense?
Yes.
Okay. And so, and also remember there is a there are a bunch, there's a base current that is diffusing over this way, which is a bunch of holes, much smaller than the number of electrons. So this is H plus. Stands for, that's like holes, hole current. And because the holes are positively charged, the direction of the current is the same as the direction of the holes. It's like a positive current, they're positively charged. So the base current looks like it's going into the base. Whoops. It looks like it's going into the base. What am I doing? Sorry, guys. Didn't erase. It's going into the base and into the emitter. So the base current is going in this way, and the collector current is coming in this way. Okay, and because we have a current coming in this way, we need to connect this resistor. If we connected the resistor, let's say if we did something like this, but I don't even know how I would do it. But anyway, it's basically the resistor you hook up to the collector emitter voltage that way. If that makes sense. Any questions about that?
So if I was to measure an amperage out of each end, I get an input from the base, input from the collector, and then an output of IC at the emitter?
Yes, yes. You'll be dumping current into the ground, and that current would be coming from this power supply, and this, either it's a power supply or input. That's exactly right. Yeah.
Cool. Thank you.
Sure. Okay, so let's see. So this is actually a good segue into looking at example 4.5 in the book. And it's actually says, okay, let's take this thing I just drew. Put in a VBE of 750 millivolts. Okay, put a output load of 1 kilo ohm. A VCE of 3 volts. Okay, if you take this, and so if you're kind of looking at the folding of this circuit, this is a little confusing, but bear with me for a little bit. So if I was gonna like redraw it like this guy here, okay, you see it's kind of like breaking, like you'll see the output is like here. Okay, so basically this guy is your current source on the output side. This guy is your current source, and then you have your R sub L. So your output is here where they touch each other. Okay, so that's your output voltage. So this is essentially, as we'll see, this is our amplifier. Okay, so we have this input and we have this output. Okay, so the example, and I'll give you guys a few minutes. Let me just to try to give this a shot before we work through it together. It says, use a I sub S of 5 times 10 to the minus 16 amps. And the question is, what is V out? What voltage is V out? Okay, so as a hint, so step 1, okay, calculate I sub C. So you have the equation for I sub C, which is a function of VBE and I sub S. So for that, you can calculate I sub C, and then you can do a KCL on this node, okay, on the output node. You have this voltage, you have this current and resistor, so you can do a KCL here and figure out what V out is. So step 2, KCL on, actually it's KVL, sorry. KVL on node V out. So why don't you guys take a crack at that for a couple of minutes, and then we'll do it together. Okay, guys. So let's try this together. So first step is, so step 1 is calculate I sub C. So you pull out your I sub c equation, which is I sub s exponential of VBE over VT. So we're making the assumption that this is forward active. So we have 750 millivolts here. It's probably enough to make this forward biased. And we have 3 volts here. Depending on the value of the collector current, it's probably enough to make this reverse bias. But let's assume that it's reverse bias, or let's assume it's forward active and see what happened if it's sort of consistent. So this is step 1, calculating it. So we just plug in, 5 times 10 to the minus 16 amps exponential of 750 millivolts over 26 millivolts, and we get something like 1.7 milliamps. Okay, so that's I sub c. Okay, so step 2, we want to figure out V out. So V out is VCE minus the voltage across the 1 kilo ohm resistor, which is I sub c 1 times 1 kilo ohm, which is 3 volts minus 1.7 times 10 to the minus 3 amps times 1 times 10 to the 3 ohms. So these guys knock each other out. So it's just 1.3 volts. Oops, let's go back to black. So V out is 1.3 volts. And then looking at our initial assumption, if I have 1.3 volts here, the collector is I don't know, like 650. Is that right? No, 550 millivolts above the base, which means that it is indeed reverse bias. So I'm in good shape. So basically, you get an output voltage of 1.3 volts. Any questions about that? Okay, so let's see. I think one last thing about collector current before we jump into the base and emitter currents is, we're saying this, but let's kind of state it like more specifically. So I sub c, this collector current, is I sub s exponential of VBE over VT. Okay, so notice there's no mention here at all of collector emitter voltage. So we have a 2-terminal device, and in fact, this thing is the current on the collector, but there's no mention of the collector voltage anywhere in this equation. That means if I plot the collector current versus the collector emitter voltage, it'll just look like a straight line. At some point, this collector emitter voltage gets small enough that base collector no longer reverse bias. Okay, but until that point, so in this whole section of VCE versus I sub c, basically as far as the collector output is concerned, this is like a current source, which we've been saying all along. But basically, that's what it looks like as far as the collector is concerned. The definition of a current source is that something that doesn't depend on its output voltage. It's just always pumping out the same current. And then this current here is just dependent on what the VBE voltage is. Okay. So we've been saying this, but it's just sort of more because we'll see these plots of collector emitter voltage versus collector current later, and I just wanted to just specifically state that.
So
Okay.
can I ask you a question?
Sure.
On the previous question, sorry to go back to it, but
Sure.
you said V out is 1.3 volts. So is that reverse or forward bias?
So so look at this. So here, so this point here, this V out is at 1.3 volts. Okay. And this VB, the base emitter voltage, therefore the base is 750 millivolts. So this P, so it's N, P, N. This P, in this PN junction is 550 millivolts below the N, which means it's reverse biased. So remember, if you had, if you look at the PN junction, if this guy is below this guy, if this guy is below this guy, this is the P side, this is the N side. So you could think of it as this being the base, this being the collector. It would make this guy reverse bias. So the collector emitter, the collector base is reverse bias.
So,
okay.
Professor, as long as the collector is greater in potential respect to the base, it's always going to be reverse bias, correct?
That's correct. That's correct. It could be 0 or higher, basically. Like, sorry, the base collector voltage. Sorry, the collector base voltage could be 0 volts or higher than 0. As long as the collector is higher than the base, it's in reverse bias. Does that answer your question?
Say it one more time.
So as long as the voltage between collector and base is greater than 0, the collector base junction is reverse bias. For a moment, you can think of it as a diode with the P side being the base and the N side being the collector. And think about if the collector, if this collector node is higher than the base node, even a little bit, you would end up being reverse bias if this point is higher. If it was lower, it would be forward bias. Does that make sense?
Yeah. So, Professor, just so that I get this, so example 4.5,
Yeah.
the voltage of the collector base is 550, right?
That's correct. Yep.
Okay, got it. Thank you.
Sure. By the way, I mean, I don't want to confuse you guys, but let me just state something. You'll see this a little bit later, just in a couple of lectures. But if you guys remember, because we had this VD on voltage, this collector could even be a little bit less than the base, and the diode would still be reverse biased because it's got to be below 1 VD on, which, if you guys remember, was like, I don't know, like 700-800 millivolts typically, and it was still reverse bias. You had to overcome that VD on to make it forward bias. So we even have more room than this. This is like a pretty conservative approach for reverse bias. Does that make sense?
Yes.
Okay, so let me tell you, one of the things you guys will see in circuit design is power consumption is very, very important in circuit design all the time. So what happens is the power consumption of, for example, of this circuit, we said the current goes from this VCE voltage source out to ground, right? So if you look at the power consumption of the current is like the power is I sub C times V, okay, which is this 1.3 milliamp, which we calculated times 3 volts. Okay, so that's, I don't know, like for, 3.9 milliwatts. Okay, so the way to reduce that power consumption, one way, is the first thing, let's say you're working for a company, they always would want to reduce power consumption. The reason is, if you're battery powered, the battery will last longer. If you are building a mechanical enclosure around this thing, it'll be less heat transfer. So all the time there's like a huge incentive to reduce power consumption. So what people will tell you during design reviews, or like your manager or whatever says, look, I have 550 millivolts here. You can just reduce your power if you bring this 3 VCE at 3 volts to 3 volts minus 550 millivolts, and you can still basically keep your transistor in forward bias. So, did you guys see what I'm saying? And you just reduce your power consumption by that much. Instead of 3 volts, you'll have 2.45 volts times the 1.3 milliamps. So there's a huge push. There'll be a huge push to reduce this voltage, and so that's why I'm saying this thing is pretty conservative. If you want to stay conservative, you can do it like that, or you can even maybe come down to VC of like, I don't know, 2 volts maybe. But it starts getting, you won't have a lot of operating margin, because in practice, when you guys are building products, you can't always guarantee that you design something like with a 3 volt power supply, it's always going to be exactly 3 volt supply. The first 100 units might be 3 volts. The 101st through 120th unit might be 2.9 volts. Just there'll be variations. Same with these resistors. There's like, depending on the type of resistor you use, your I sub S's in your transistors, when you build your product, there'll be some variation there. So you want to build margin here so that you keep this in forward active. But where you'll get pushed as engineers, so the people making business decisions are interested in like things like reducing power consumption, things like that. So where it'll get pushed is how far you can push that and still have a safe product that meets the specs. Okay. All right. So let's, if there aren't any other questions, let's start talking about the base and emitter currents. Okay, so I'm gonna go. Well, I'm just gonna mention this, but don't worry about this too much, because I think we've already beat this one slightly to death. But if you go back and look at equation 2.97 in the book, so this is back in the PN junction, right? We'll see that the current. So let me just draw this before I get into this. So remember that we said when we have NPN and we made this N plus, we made the doping of this guy high. So this is this doping compared to this doping. We made this high so that we guaranteed we would have a really big electron current compared to the whole base current. Okay, so right now we're trying to figure out what this is, come up with an expression for this. So I sub so this total current. So if we look at the current, just look at the current of this junction. So it'll be this current plus that current. It's gonna look like, let me write it up. So this is from, I think we'd looked at this back in, slide deck too. So that current is, as a function of so this is as a function of the acceptor. So this will sort of be the whole current. Exponential of Vf over Vt minus 1 plus this will be the electron current. Okay, so if you look at it, the same sort of total current, so this is the total current across the current across the base emitter junction. Okay, so basically the current, this current going across this junction is made out of, so this I total is made out of a whole current plus an electron current. And this is the equation for that. So if I look at this I total, so it is proportional to N, the whole current is proportional to N sub A, and the electron current is proportional to N sub D. And so, again, I think we've talked about this, we're like beating this to death, but it's very important that by making the doping concentration of the emitter, this N sub D, much, much higher than the doping concentration of the base, we make sure that basically the electron current is much, much higher by this ratio of ND to NA. Notice everything else here between these two things that make up your total current, everything else is the same. The only difference between them is the doping concentration. So the higher the doping concentration of the emitter, the bigger portion of the current is the electron current. And so you would like, if you look at this transistor as like a 3-terminal device, for reasons you'll see later. So this would be the emitter, collector, and this would be the control. So it'll be the base. You kind of want a small thing here calculating, a small thing here controlling a big thing here. That'll give you the ability to not load down whatever's driving this guy. Some other thing, let's say there'll be a microphone or something driving this amplifier here, or this transistor that makes the amplifier. You don't want to force that microphone, for example, to source a lot of current, whereas you want that output to be very high. So that's how you sort of get a big gain out of it. So it's a good transistor is something that has a large collector current that's being controlled by a small base current, and basically achieve that by having this difference in ND and NA. Okay, so what happens is this ratio ends up normally being so high that, in a typical basis, you get maybe like something like, say, 200 electrons for each hole. Okay, so it's like a really lopsided current. You get a lot of electrons for very few holes. And that ratio is called, something more goes into it, but that ratio is called the beta. Okay, is the sort of the ratio of electron to a hole current. Okay. And again, it's completely determined by the doping, the difference between the doping concentrations. Okay, so the definition, remember the hole current is equal to the base current, because that's the current that's the base has to deliver. So I call that I sub B. And the electron current is the collector current. Is equal to I sub C. Okay, so another way to write this beta is by saying I sub C is equal to beta I sub B. Okay, so you can kind of think of the collector current. This is one way to look at this, is the collector current is an amplified version of the base current. Okay, so you can think of this guy as, as a current amplifier from the base to the collector. And this beta, it's, depending on the transistor, et cetera, is anywhere between 50 and like 200. Okay, or these are like typical values. Okay, or you can think of as base current being I sub C over beta.
Professor, I have a question.
Sure, go ahead.
It's beta, right?
That's right. Yeah.
Okay, the beta value, what does it depend on?
It depends on, to first order, it depends on the doping concentration of the emitter and the doping concentration of the base.
Okay.
And to some extent, so the secondary effect is, if you guys start taking semiconductor classes, you'll see there's some recombinations. A few of these electrons will recombine with holes here. So not all the electrons will make it all the way through. It'll depend on the recombination rate in the base, but that's sort of a secondary thing. Most of it is the doping concentration differences between the base and the emitter.
So if it's like on the lower end, do we say that it has more concentration on the base or emitter, or vice versa?
Yeah, or it could be you're getting more recombination. Yeah,
okay.
That's right.
Thank you.
Sure. And then one, I think, it's like a good question. So let's see. So one of the first mistakes you'll make if you'll design a circuit with these things is try to use in your spec sheet, it'll say beta is equal to 100, and you're going to read that as an exact value of beta. That's like a really bad idea, because there'll be variations in beta. So if the key to designing these circuits is to not design them for one point, but this beta will be different slightly from transistor to transistor. Even the same part number, you buy the stuff from the same manufacturer, again, same part number, there'll be some variations in the beta. You can just sort of count on beta, and you'll see this in a lot of circuits, is you count on the beta being a high value, but do not count on it being an exact value. This is when you design a product now, because you'll even see it in the lab, right? The spec sheet will say 100, but if you're making a circuit that's relying on that being exactly 100, you're like, it's bad news. You should make a circuit that's the manufacturer a lot of times will tell you the variations of the beta. But let's say you should make a circuit that works when beta ranges from 90 to 110, that kind of thing. Same with I sub s. When they tell you here's a certain I sub s, which is the other thing this thing relies on, you always expect some variations around I sub s, but you want these combination of things to be high values, and you'll see why. But anyway, so hopefully that didn't confuse you guys too much. But don't these are values, like ranges of values for beta that you would expect, but from device to device there'll be variations. Okay, so that's the base current. So the takeaway here is the base current is a lot less than the collector current. Okay, so let me just, that's always the case. I mean, as long as you're forward active. So base current a lot smaller than current. And sort of for hand calculations and stuff, you just, it's like a beta smaller. Okay, so now let's look at so that's the base current. This is the equation for it. Right here. Okay, so now we want to look at the collector current. And the collector current, the emitter current. So you can see this guy is the collector current, right? This guy is the base current. So if we just look at this as a circuit, so if I redraw this thing as a circuit, so I had this collector current and I have this base current. So, and we said all of that stuff is coming out of the emitter. So by KCL says I emitter is just I collector plus I sub base. Okay. And that's sort of all it is to it, is I sub emitter is I collector plus I sub base. Okay. And then if you look at this a little bit more, so this is I collector, and if you write I sub base as the I sub c over beta, we'll get this as plus I sub c over beta. So this is equal to I sub c 1 plus 1 over beta. And what I want to say about that. Okay, so, and notice this is, let me rewrite, this is I sub c of beta plus 1 over beta. And let's see. So if there's another thing called alpha. I didn't want to trouble you guys with that, but I think it's just sort of, it's taking this value and calling it alpha. But look at this thing. So we said so up here we said that the base current is a lot smaller than the collector current. But if you look at this ratio of I sub c for the emitter current, so if you look at B plus 1 over beta, if beta is large, then beta plus 1 over beta, or this thing, is approximately 1. Because, you get this thing being large, this thing being large, and they're both much bigger than 1. So it'll just look like beta, so this will approximately equal to beta over beta, or approximately equal to 1. Okay, so the emitter current is very close to being exactly like the collector current. So a lot of times a good approximation, unless the problem asks for you to actually calculate it, is that the emitter current is approximately the same as the collector current. So that's always a good approximation. Okay. Any questions about the emitter or the base current?
So, Professor, in general,
Oh,
the base current is always the smallest, and then after that comes the collector current, and then the emitter current is very close or slightly larger than the collector current, right?
that's correct. Slightly larger.
Oh, okay. Thank you.
Yeah, it might be. So like one way to look at it is if you're gonna do back of the envelope calculations, like a good approximation is beta is equal to 100. That's like something you'll see all the time as something people throw out. It's sort of along saying VBE is equal to 800 millivolts. It's not always 800 millivolts, but like it's like something you'll see a lot, or VD on being 800 millivolts. So these are all sort of good approximations. And if you use that approximation, the base current is like 1% of the collector current. And the emitter current is like, or the collector current is 99% of the emitter current. So that's like, if that helps. So the emitter and the collector current, you can think of them as being about the same value. And like you said, the base current being much, much smaller.
All right. Thank you.
Sure. So actually that's like a good segue into this next example to give us some idea of what approximately these things look like. So this says, we have a bipolar with I sub s 5 times 10 to the minus 16, and it's in forward active. Okay, with base emitter being equal to 750 millivolts. If beta is between 50 and 200 because of manufacturing variation. That's a lot of variation, but what the heck? Variations calculate min and max terminal currents, which are, I sub C, I sub B, and I sub E. So why don't you guys give that a shot for a few minutes, and then we'll hit it together.
So before you leave, the only thing that's varying is the beta, correct?
That's correct.
Okay, thank you.
Sure. So as like a hint, basically so step one is use your equation, calculate I sub C. And then step two is using I sub C and beta to calculate I sub B and I sub B, sorry. And step three, use I sub C and I sub B to calculate I sub E. Okay, guys, let's try to do this together. So first thing, you should just be like, as long as you're in forward active mode, you can bust out your equation. I sub c is I sub s exponential of VBE over V sub t. So according to the parameters for this thing, there's no variation there, right? So it's 5 times 10 to the minus 16 for I sub s exponential of 750 millivolts over 26 millivolts. Okay, and then this gave us around 1.7 milliamp. Okay, so that's not varying. So I sub c is always ends up being 1.7 milliamp. So this is step 1. Step 2, we're going to calculate I sub b, which is I sub c over beta. But there's a high value for I sub b for beta being, the high value of I sub b is for beta of 50, and the low value is beta of 200. Okay, so I sub b is between 1.7 milliamp, which is this collector current, divided by the 200, which is the high beta value. It's going to be less than 1.7 milliamp. Again, the collector current divided by 50, which is the low beta value. So I sub b ranges between 8.43 microamps and 33.7 microamps. Okay. And step 3, is calculate late I sub e, and I sub e is just equal to I sub b plus I sub c. Now I sub b is the only varying thing, so I sub e is going to go between 1.693. That's probably too much precision, but 0.719 milliamps. Whew. Okay, so a few notes here about what we're seeing. Notice that I sub c is 1.7 milliamp, and I sub b is in the microamps. Okay, so this is sort of single-digit milliamps. This is maybe double-digit microamps, so significantly less than the collector current, and also significantly less than the emitter current. Emitter current is also in the sort of the 1.6 milliamp range. So I sub b is to look at how much lower it is. The other thing, so maybe I should just write that. So I sub b much smaller than I sub c and I sub e. So that's observation 1. Observation 2, look at the variation on I sub e. So the I sub e is, it's not varying that much. It may be changing by like 1%. Okay, but look at the variation in I sub b. The I sub b is changing by I don't know, by like a factor of 3, like 3x or more between the low and the high. So basically there's a big variation in I sub b, but not a big variation in I sub E. Okay. So those, I think those kind of things that I think it's fair to say you'll see these sort of over and over again. Any questions about that? Okay, if not, maybe I will.
Professor, yes, I did have a question.
Sure, go ahead.
So for the current in the emitter, it was 1.7 milliamps, the lower end, plus 8.43 microamps, right? Lower end.
Yes. No, wait. Is that right? Hold on. Hold on. Let's see. Maybe I screwed this up. So on the high end, it's, yeah. Wait. You're right. I did have a wrong calculation here. So this should be 1.733, and this should be 1.708. Is that what you mean?
Yeah. Oh, okay. Just making sure. I thought it was wrong.
No, you're correct. Sorry, I screwed that up. I went too fast there. Thanks for catching that.
Thank you.
Any other questions about that? Okay, so I'm just gonna then draw the rest of the bipolar transistor. So we have, again, we have our base collector and emitter. And so we already drew this is in the forward active. So this is the emitter. It's the shared node. This is I sub s exponential of VBE over VT. So in the output, when you're in forward active mode, in the output where the collector is, it looks like you have a current source, which the output of which depends on the input VBE. And on the VBE side, it looks like you have a diode going from the base to the emitter. And the equation for this, and then basically this diode we put in here to have some way of showing I sub B. So what we do for I sub B is, notice we have I sub S here. So what we do with I sub B is that we say I sub S over beta exponential of VBE over VT. This is the base current. Okay, so this diode here, this diode is placed there. So placed to represent base current. So that way, when you have like your device driving this transistor, it'll see that it will need to produce this amount of base current. Okay, which is going to be beta times smaller than the collector current. Okay.
Oh, I see. So that's why it's I is exponential, because IC is that, right?
Yep, that's exactly right. So we're basically this diode. So this is like a cheesy way of trying to create this base current. So we're just taking the collector current and dividing it by beta.
Okay.
To sort of, in our model, have a base current representation. Okay. So finally, and I'm going to stop here. is, so as you've seen in our examples, etc., the way to solve the problems is this. So I think the book calls it a chain of dependence. So of course, some problems could be trickier than other ones, but this is typically what you want to do. So first, you take the VBE and you calculate I sub c. So that's the first thing you do. And that equation is I sub c is I sub s exponential of VBE over VT. Okay, so that's step one. And then step two is use I sub c to calculate I sub b. And the equation use that is just I sub b is I sub c over beta. And use I sub b and I sub c to calculate I sub e. And that is just I sub e is equal to I sub b plus I sub c. So start with VBE, calculate the collector current, divide the collector current using this exponential equation. Divide the collector current by the beta to get the base current, and then the sum of the base and collector currents make up your emitter current. So those are the sort of a typical steps to take.
Usually they'll give us a beta, right?
Yeah, I'll give you guys a beta. Yeah. Almost always they'll give you a beta and I sub s, I guess.
All right. Thank you.
Sure. Speaking of that, Amber got her wish. I put on a bunch of problems, homework problems. Boy.
Thank you. I saw that.
Oh, my pleasure. No, I think both of us are like dreading this because I got to do it with you guys. So it goes a couple of weekends there. So anyhow, guys, if there aren't any questions, I'll have a great weekend and I will talk to you guys on Tuesday.
Thank you for everything, Professor.
Take care.
Thank you, Professor.
Bye.
See ya, Professor. Have a good one.
Bye. Thanks.
Good weekend. Bye-bye. God bless. Bye-bye.